Welcome back, grade 10s. In today's lesson, we continue with the topic of matter and material, but we're starting on a new section, which is states of matter and the kinetic molecular theory. Let's go through the objectives. We need to understand the concept of standard temperature and pressure, or STP, and how this affects the melting and boiling points of substances. We are going to list and characterize the three states of matter, which is solid, liquid, and gas, and we're going to describe each of these according to the particle model of matter. We will define melting, boiling, evaporation, solidification, condensation, sublimation, and reverse sublimation or deposition. We will identify the physical state of a substance at different temperatures, given its melting point and its boiling point. We will learn how to draw and interpret a heating and a cooling curve, and we're going to explain the heating and the cooling curve based on the kinetic molecular theory. And lastly, we're going to understand and describe Brownian motion and diffusion, again based on the kinetic molecular theory. So let's start off by understanding standard temperature and pressure, or STP. Now, air particles that surround us, they move quickly and randomly over large distances, and those air particles press against objects and they bounce off them. So air particles are constantly colliding against you and bouncing off of you, and that exerts an air pressure, also known as atmospheric pressure. So there is air pressure or atmospheric pressure exerted on all objects due to the air that is surrounding them. Now, when we talk about standard temperature and pressure, well, that is the atmospheric pressure or the air pressure that is exerted by air particles when, firstly, the surrounding temperature is 0 degrees Celsius, which is equivalent to 273 degrees Kelvin. And secondly, when the air pressure is at 1 atmosphere, which is equivalent to 101 kilopascals, and that is the surrounding pressure at sea level. So when we talk about water having a melting point of 0 degrees Celsius and water having a boiling point of 100 degrees Celsius, that applies to water's boiling point and melting point at standard temperature and pressure. And again, what that means is that water will melt at exactly 0 degrees Celsius and it will boil at exactly 100 degrees Celsius if the temperature surrounding the water, if the atmospheric temperature is 0 degrees Celsius, and if you're trying to boil or melt that water at sea level, where your surrounding air pressure is 1 atmosphere. So if your surrounding temperature is not 0 degrees Celsius, or your surrounding air pressure is not 1 atmosphere, then water will not melt at exactly 0 degrees Celsius and it will not boil at exactly 100 degrees Celsius. It will deviate slightly from those temperatures. So whenever we talk about the boiling point or the melting point of a substance, that automatically applies at standard temperature and pressure. So again, when we say that water boils at 100 degrees Celsius, what we mean is that this is the boiling point or the boiling temperature of water at standard temperature and pressure, at STP. So what that means is that water will boil at 100 degrees Celsius if the surrounding temperature, the air temperature is 0 degrees Celsius, and the surrounding pressure is 1 atmosphere, which is equivalent to 101 kilopascals, or more specifically 101.3 kilopascals. Atmospheric pressure changes with changing elevation or altitude. So your elevation or your altitude means how high are you above or below sea level. Now, if we consider these diagrams over here, what can we see happens to air particles as we increase our elevation or as we move higher up? Well, we can see that the air becomes thinner. One of the reasons for that is that there is a weaker gravitational pull pulling the air particles closer to Earth when the elevation is greater. So we know that at higher altitudes, we actually have lower air pressure because the air is so much thinner. It is less dense, whereas at lower altitudes, we have a higher air pressure. So as we can see, as we go higher and higher, the air becomes thinner. So what is the relationship between elevation and atmospheric pressure? The relationship is that as elevation increases, the atmospheric pressure decreases. Atmospheric pressure also changes with the changing surrounding temperature. When the air around us is cold on a cold day, is there a higher or a lower atmospheric pressure? Well, on a cold day, the particles that make up the air are closer together because they have less kinetic energy. On a hot day, the particles move faster and further apart. So there will be a stronger atmospheric pressure acting on objects on a cold day. As we can see, the air particles move faster and further apart as the temperature increases. So what is the relationship between temperature and atmospheric pressure? Well, as the temperature increases, the atmospheric pressure decreases. The boiling point of a liquid, that is a very, very important definition that's going to come up over and over again. So you're going to write down the definition and I'll explain what it means shortly. So the boiling point of a liquid is the temperature where the vapor pressure of that liquid equals the atmospheric pressure. So what does this mean? So as we already discussed, there is an atmospheric pressure or an air pressure that is exerted by the surrounding air particles on all objects. So there is an atmospheric pressure acting on the liquid inside this container. The vapor pressure is the pressure that is exerted by the liquid particles. Now, some of these liquid particles might have enough energy to escape the liquid as a gas. They need to gain enough kinetic energy in order to escape the strong intermolecular forces of attraction within the liquid and turn into a gas where the intermolecular forces of attraction are extremely, extremely weak. So again, the atmospheric pressure pushes down on the liquid, and the vapor pressure is the pressure exerted by the liquid to try to escape the liquid as a gas. For the liquid to boil, this vapor pressure needs to just overcome the atmospheric pressure of the surrounding air, which would then allow this liquid to boil and escape into the surrounding air as a gas. As already mentioned, when we talk about water having a boiling point of 100 degrees Celsius or iron having a melting point of 1538 degrees Celsius, those values are only true at standard temperature and pressure. So if the surrounding conditions are not exactly at standard temperature and pressure, then the boiling point and the melting point of that substance will deviate from what we call the standard boiling point and the standard melting point. And the standard boiling point is the boiling point that's experienced at standard temperature and pressure. The standard melting point is the melting point experienced at standard temperature and pressure. If we have a greater atmospheric pressure, meaning that the air particles are exerting a greater pressure on objects, so that would be on a cold day or at very low elevations, what is going to happen to the vapor pressure? If the atmospheric pressure is pushing down harder, then the vapor pressure needs to overcome that, which means that the vapor pressure will also be greater in order to overcome a greater atmospheric pressure. So what that means is that the boiling point of that substance, which is the temperature at which it will boil, it will become higher. Because the liquid particles need to exert a greater vapor pressure when the atmospheric pressure is greater, it means that it will reach boiling point at a higher temperature. On the other hand, if the atmospheric pressure is lower, so on a hot day when the particles are further apart from each other or at a high elevation where the air pressure is lower because the air is thinner, then in response, the vapor pressure will also be lower. And if the vapor pressure is lower, meaning that the vapor pressure needs to overcome a lower atmospheric pressure in order to boil, then that means that the boiling point will also be lower. Johannesburg is about 1.7 kilometers above sea level. On a warm day in Johannesburg, water will boil at around 94 degrees Celsius. So because the conditions in Johannesburg are not at standard temperature and pressure, that means that water will not boil at exactly 100 degrees Celsius. The other thing we need to keep in mind as far as the boiling point of water is concerned is that when we boil water that is impure from the tap. So even at standard temperature and pressure, tap water will not boil at exactly 100 degrees Celsius. Very interesting is that Mount Everest, which is nearly 9 kilometers above sea level, there the water will boil at around 70 degrees Celsius. Because the air is so thin at the top of Mount Everest, regardless of the fact that it is so cold at the top of Mount Everest, your water will boil at 70 degrees Celsius, meaning that you can't have a cup of coffee that is warmer than 70 degrees Celsius at the top of Mount Everest. Water cannot actually reach a higher temperature than 70 degrees Celsius. It will boil at that temperature at the top of Mount Everest. Now, this whole idea works similarly for melting. If you have a high atmospheric pressure on a solid, that high pressure keeps the particles of the solid close together in an organized pattern. A high atmospheric pressure makes it more difficult for the particles in the solid to pull apart from each other and turn into a liquid. So if the atmospheric pressure is less, then the particles that make up the solid can move further apart from each other more easily, turning the substance into a liquid more easily. So that means that the melting point will be lower when the atmospheric pressure is lower. Therefore, if the atmospheric pressure is greater, then the melting point of that substance will also be greater or higher. And that's because if there is a stronger air pressure acting on that solid needs to exert back a higher pressure in order to turn into a liquid. If the atmospheric pressure is lower, then the melting point of that substance will also be lower. That brings us to the end of our discussion on standard temperature and pressure. And now we're going to learn about the 3 states of matter. Solid is a state in which matter keeps a fixed volume and shape. Liquid is a state in which matter keeps a fixed volume, but due to gravity, the liquid will always take on the shape of the container that it is in. And gas is a state in which matter distributes itself spontaneously and uniformly across the entire volume of the container that it is in. In this figure, we can see water in all 3 states. We can see ice over here. There's liquid in the water, and clouds, in fact, are condensed water, so it's in the liquid state. And then we've got water vapor, which is not something that we can actually see, but we know that there is water vapor around us in the air, in the gas state. Whatever the state, the water molecule remains chemically identical as H2O. So there's no chemical change when there is a state change or a phase change. Other substances can also change their state or their phase. So metals can be melted so that they can be molded, so they change their state from solid to liquid. Again, they remain chemically identical. It is just their state or their phase that has changed. Solid rock melts to form molten lava. So lava is just rock in the liquid phase, and that's what feeds volcanoes. And in the case of a nuclear explosion, it gets so hot that rocks can even turn into vapor. What is key to realize is that in all these examples, the physical state of the substance changes, solid, liquid to gas, or vice versa, but the chemical composition of the substance remains the same. So, for example, the H2O, when it is in solid form and when it is in gas form, is still chemically one oxygen atom bonded to 2 hydrogen atoms. Now, if we want to change the state of a substance, what's the most common way of doing that? We can heat up the substance, or we can cool it down by taking away heat energy. So heat is a type of energy that we can either add or we can take away in order to change the state of a substance. By heating up a substance, we're actually giving the particles more kinetic energy. So we allow them more energy to turn from the solid phase to the liquid phase and to the gas phase. By cooling it down, we're removing that heat energy, meaning that the particles lose kinetic energy, meaning that those particles can then change state from a gas to a liquid and to a solid. So when the particles lose kinetic energy, they are forced to move closer together. When they gain kinetic energy, they actually are forced to move further apart. So really, the changing of state of a substance just involves the distances between the particles. Now, we can actually help change the state of a substance, not with heat alone, but with pressure as well. So we can influence the melting and boiling point of a substance by changing the pressure. So, for example, at standard temperature and pressure, meaning that the surrounding temperature is 0 degrees Celsius and the surrounding atmospheric pressure is 1 atmosphere. Under those circumstances, oxygen will solidify at minus 219 degrees Celsius. But what happens if in a lab we increase that atmospheric pressure to 10 atmospheres? So we make the pressure 10 times stronger, meaning that we force the particles of oxygen much closer to each other. And so if we do that, we only need to reduce the temperature to minus 8 degrees Celsius in order to turn oxygen into a solid. And that's because along with the decrease in temperature, which decreases the kinetic energy of the particles, which means that they move closer together, we also increase the pressure, which physically forces the particles to move closer together. The particle model of matter is a model that explains the arrangement of particles in solids, liquids, and gases. Now, whether the substance is in the solid, liquid, or gas phase, the particles are always moving. Even in the solid phase, where the particles only vibrate in their position, there's still movement. And what type of energy is associated with that movement? Well, it's kinetic energy. The particles of a solid are associated with the lowest kinetic energy, and the particles of a gas are associated with the highest kinetic energy. We cannot see the particles that make up matter, so there's no way that we can measure their speeds. So how do we measure the kinetic energy of a substance? It is simply based on temperature. So the temperature of the substance will give us a measurement of the kinetic energy of the particles that make up the substance. At room temperature, which is around 23 degrees Celsius, the air that you breathe is in gas form. The water in your water bottle is in liquid form, and the iron leg of your desk is in the solid phase. Now, what that means is because all three of these substances are sitting at the same temperature, they're all sitting at room temperature, it means that the particles that make them up all have the same kinetic energy. Now, even though air is a gas, water is a liquid, and iron is a solid, because they're sitting at the same temperature at room temperature, it means that the kinetic energy of the particles is the same. Now, obviously, in the case of the iron, where the particles are vibrating in their position, they don't have very long distances to travel, but their speed is the same as the speed of the particles that make up the air, even though those gas particles have bigger distances to travel. So that's because the particles all move at the same speed, even though there's a different distance between the collisions, at the same temperature. But if we're talking about a given substance, let's say we talk about water. Water in the solid phase has a lower kinetic energy than water in the liquid phase, and water in the gas phase has a higher kinetic energy than water in the liquid phase. Another example, iron in the gas phase has more kinetic energy than iron in the solid phase. Now, that makes sense because in order to turn iron, which is a solid at room temperature, into a gas, we need to increase that temperature, which means that we increase the kinetic energy of the particles. Water in the gas phase has more kinetic energy than water in the solid phase, and that makes sense because in order to turn water into a solid, we need to reduce its temperature, and by reducing the temperature, we reduce the kinetic energy of the particles. Here are some important definitions for changes of state. The change of state from a solid to a liquid is called melting. The change of state from a liquid to a gas is called boiling. The change of state from gas to liquid is called condensation. The change of state from liquid to solid is known as solidification. We rather use the word solidification, which is more scientific, than the word freezing. There's also a change of state from the solid phase to the gas phase, meaning that the liquid phase is skipped. And the two main examples are dry ice and iodine. This change of state is known as sublimation. So over here we've got frozen carbon dioxide that is turning into carbon dioxide gas. There is no liquid phase. And over here there is solid iodine turning into a gas phase. There is no liquid phase. The opposite of that, changing from gas to a solid without the liquid phase, is known as deposition or as reverse sublimation. Another very important concept that we need to understand is that the solidification point or the freezing point and the melting point of a substance is the same temperature. And the condensation point and the boiling point of a substance is also the same temperature. What do I mean by that? If I ask you, what is the freezing point of water? What is the melting point of water? Well, the answer to both of these will be 0 degrees Celsius. If I ask you, what is the boiling point of water? What is the condensation point of water? Well, the answer to both of these will be the same. It's 100 degrees Celsius. How is that possible? So the freezing point and the melting point of a substance is the same temperature, and the condensation and boiling point of a substance is also the same temperature. Let's start with a piece of ice. Let's start with that ice at minus 18 degrees Celsius. Minus 18 degrees Celsius is about the temperature of your freezer. Now, if we increase the temperature of that ice from minus 18 degrees Celsius to, let's say, minus 2 degrees Celsius, at minus 2 degrees Celsius, the ice is still in pure solid form. However, this ice is warmer than this ice. The particles that make up the ice at minus 2 degrees Celsius have more kinetic energy because this temperature is higher than this temperature. Now, let's increase the temperature to exactly 0 degrees Celsius. At exactly 0 degrees Celsius, we will still have solid ice. It is not going to start melting until we've increased the temperature to just above 0 degrees Celsius. At that point, from 0.1 degrees Celsius onwards, the ice will start to melt. If I increase the temperature to 20 degrees Celsius, of course, then the ice will melt, but it will melt faster than it would at 0.1 degrees Celsius. Again, because all that extra heat in the environment provides more kinetic energy for the particles. Now, let's say that we start with a glass of water at room temperature at 23 degrees Celsius. Now, if we're going to reduce the temperature of this water down to, let's say, 4 degrees Celsius, which is about the temperature of your fridge, well, now you're still going to have water, but it is going to be a much colder glass of water. Now, let's carry on reducing the temperature all the way to 0 degrees Celsius. And what you're going to find is that at 0 degrees Celsius, this water is still in full liquid form, and it will not start to solidify until you reduce it to minus 0.1 degrees Celsius. If we start with ice and we increase the temperature, at 0 degrees Celsius, it will exist as a solid. And just above 0, it will start to melt. If we start with liquid water and we decrease the temperature, then at 0 degrees Celsius, it will exist as a liquid. And just below 0 degrees Celsius, it will start to solidify. So now we understand why the solidification point and the melting point of a substance are actually the same temperature. And exactly the same thing applies to the condensation point and the boiling point of a substance. If we start with liquid water and we increase the temperature all the way to 100 degrees Celsius, at 100 degrees Celsius, it will still exist entirely as a liquid. It wouldn't have started to boil yet. It will just be a very, very hot liquid. I would need to increase the temperature to just above 100 degrees Celsius to get my substance to start to boil. If I start with water in the gas form and I decrease the temperature, then at 100 degrees Celsius, that water vapor will still exist entirely as a gas. It wouldn't have started to condense yet. And just below 100 degrees Celsius, will the substance start to condense? Will the water start to condense? So if I start with water as a liquid, then at 100 degrees Celsius, it will still be a liquid. If I start with water as a gas, then at 100 degrees Celsius, it will still exist entirely as a gas. That is why the condensation point and the boiling point of a substance is the same temperature. It really depends on the state of the substance that we started with. That will then decide what it will exist as at its freezing point or melting point, or at its condensation point or boiling point. And the last thing we need to understand when it comes to the three states of matter is the difference between boiling and evaporation. Those two words cannot be used interchangeably. We talk about the boiling point of a substance at standard temperature and pressure, but evaporation is different. Boiling takes place at the boiling point of a liquid when bubbles of vapor form in the liquid. When a substance boils, so let's say I'm boiling water in a pot over here, wherever I apply the heat is where it will start to boil, because that's where the temperature is going to increase first and foremost. Now, if this is water at standard temperature and pressure, at just above 100 degrees Celsius, bubbles will start to form in the liquid. And what is inside this bubble of gas? Well, if inside here we've got pure H2O, then inside this bubble of gas is pure H2O also, but in gas form. Now, gases are less dense than liquids. That bubble is going to float to the surface because of its lower density, and it's going to pop open at the surface of the liquid, and all the H2O gas that was trapped in this bubble will now be released into the atmosphere as water vapor. So boiling takes place at the boiling point of a liquid when bubbles of vapor form in the liquid, and the bubbles of vapor contain whatever substance this liquid is made of. Evaporation, on the other hand, takes place at all temperatures, not just at the boiling point. So, for example, when you leave your clothes to dry outside, hanging them on the line in the sun, you'll find that your clothes are going to dry even though they haven't reached the boiling point. If you leave water, a glass of water on a desk, the water level is going to drop even though that water never reached the boiling point. That tells us that the process of evaporation takes place at all temperatures, and it takes place at the surface of the liquid. The way that it works is that these particles on the surface of the water have the potential to escape the liquid as a gas. And that happens if one of the lower lying particles bumps off a surface particle with enough energy to give it enough kinetic energy to escape the liquid and turn into the gas phase. So the difference between evaporation and boiling is summarized in this table. Evaporation takes place at all temperatures, while boiling only takes place at the boiling point. Evaporation takes place only at the surface of the liquid, whereas in the case of boiling, bubbles of vapor form within the liquid, and that vapor, with its low density, will rise to the surface and release large quantities of vapor. Boiling is a much faster process than evaporation.